So we're talking about energy of a spring here. And one of the things that we've said in the past here is that one of the big deals here is that when we talked about kinetic energy, one of the things that we saw here is that kinetic energy was special because that was the work stored in motion. But now we're going into a different class of energy, and potential energy is the work stored in position. So if I talk about the work stored in a spring, we talked about the work done by my hand. And if I look at the work done by my hand that stretches the spring, one of the things that I already said here is that anytime you do work, the work doesn't disappear. The work energy says that it goes into energy. So in other words, the work of my hand added energy to the spring that resulted in the stretching of the string. The question is, where did it go? We know that the work doesn't disappear. So what we say here is that it didn't go into kinetic energy because we started and ended at rest. So therefore, it had to be stored in the stretching of the spring. So when you look at the rungs of the spring, they're spaced out further. But just to re-stress that idea, right? The energy of the spring, I did work, I clearly increased the energy of the spring. So the question is, we now change our viewpoint of how we want to view it. And the way we do here is that we focus only on the mass spring system. And if we focus on the mass spring system, that means that within the system, the only force acting on the spring is the spring force. The force of the hand is external to the system. The spring force is internal to the system. And so note that this is a really big change in viewpoint. So if I go and I reinterpret the whole thing that we did before, is that we now know that the spring clearly does negative work because you can see that the spring force is opposite the direction of the displacement. And as a consequence, ooh, that's a typo right there. Look at this. The work of the hand is positive, so it goes in that direction. And then the work of the hand, even though it's external, is actually increasing the energy. So what we're finding here is that if I look at this picture-wise, the work of the hand, which is external, that's what increased the energy of the spring. But if I look at the internal forces, it's the negative work of the spring that increased the energy of the spring. So the more I stretch the spring, the more I'm converting work into energy. But I get this negative work that resulted in an increase in potential energy. So one of the biggest problems with this type of new energy that we're starting to work on, potential energy, is that all potential energies of the universe always have what? They have a negative sign. And that negative sign is really disturbing in the sense of just talking about increases in energy. But it's because we're now isolating things from external to internal. And that negative sign pops up very naturally. And the same thing happens with gravity. I could have a force of my hand, force of gravity, and then if I said the force of my hand is external, the force of gravity is internal, you could see that the force and the displacement are in opposite directions. So I get this negative sign again. So this is a very different class of energies that we're looking at. And so what we're saying here is that the precise definition of potential energy now is that we define a potential energy function U, which is fairly universal. And this can only be defined by a force that's doing the work that is conservative. So now I need to answer this question. What is a conservative force? And as you can probably already guess, It has nothing to do with politics. This language has been way before the word conservative has come up in politics like this. So this guy, you're going to see here is that in order to be a conservative force, these forces must satisfy two conditions. Okay, here we go. Here's condition number one. So this is a fairly theoretical conversation that we're doing here. So I'm not going to try to dwell on it too much. One is condition one. Well, what's special about condition number one? Well, what's special about condition number one, it says that a conservative force, if it's done, if a conservative force is doing work around a closed loop, that work is zero. Okay, let me try that one more time. So it says this here. So the first condition tells us this. A conservative force doing work around a closed loop is zero. What do I mean by that? Well, I'm going to do work, and this force is conservative. And the way we typically talked about a closed loop is we put a circle around the integral. This tells me that this is a closed path. What is a closed path? That its starting and ending point are the same. So then I have F conservative, and then I'm doing a loop around this thing. This guy is zero. And so what we're saying here is that it goes something like this here. And I think probably the easiest thing is to think about examples. So I want to show you two examples. Okay. The first example is gravity that I want to think about here. And what I'm going to do here is that I'm going to automatically start drawing the energy picture of gravity. And then I'm going to start talking about the energy picture of the spring. So the first one I'm going to look at is I want to look at gravity. So what I'm going to do here, in this case here, is I'm going to toss a ball up, that comes down. Of course it comes down, but just trying to be clear. So what's my picture here? So my picture here is that I have a red ball, right? It's going to go up, and then it's going to go up to that height right there. So what I'm seeing here is that the ball is moving in this direction. And then I start to look at the forces here. Well, I know that if I look at the force, I'm saying that this force is internal to the system. So what I mean by that is that I have what? I have my ground. And then I'm going to pick my system in such a way that my system, so I think about my system here, and I say that the system is equal to Earth plus ball. And when I look at this, I note that the displacement is going up like this here. So right away, we can see that there's negative work. And then, of course, what happens to the ball? You know what? I think I'm going to move this over here just because I want to Ah, let me make this black. So it looks like this here. And then, so what's going to happen here? Well, then the ball turns around. And as the ball turns around, I still have my same system. So now the ball's going to do what? It's going to move this way, and it's going to come all the way towards the ground. And of course, we have this scenario right here. So our picture then is that this guy's now going in this direction. So now I have what? I have the force of gravity. I have my displacement in this direction. Gravity does positive work, and it looks like this, right? So in other words, here's where I start. Here's where I end. So when I look at the work here, one of the things that we really want to pay attention to here is that the network in this scenario here is really going to be what? The work going up plus the work coming down. And if I look at this team, I can see that this guy, the work of gravity in this case is negative. The work in this case here, when I'm still within my system, that work within the system is what? Positive. So I should see what? Minus the force of gravity. And then there's a height change. And then coming back down, that's positive work. So it should be mg delta y. So therefore, this guy is 0. Just to be stressing here, right? One, there's negative. One is positive, just because of the sign of the works here. Now, one of the things that I really want you to start doing here is that the picture that I'm showing you here is that this picture is a Newtonian force picture. But that's the old way of viewing things. We want an energy picture. And what we're saying here is that in this case, what you're seeing here is that, note that if I look at the work of gravity, we already know is the change in potential energy. And for gravity, we're going to write this as the change in gravitational potential. And one of the things that you can see here is that the work of gravity is then going to be proportional to mgy. And you could see that from that picture here. So now if you look at the energy picture, which I won't describe in detail here, you could see that the work of gravity is proportional to y. So if you're looking at this thing, what you're seeing here is that gravity in the energy picture looks like this here. This guy is an energy ramp. So look at the ball. Where does the ball start off? It starts right here. And what does the ball do? It goes up. How high does the ball go up? Well, it goes up until it's sort of like it stops. Just like up here, we see that the ball has stopped, and that's v equal to 0. It stops until it goes to v equal to 0. And so what does it do? Then the ball comes back down. So the work going up is exactly the work coming back down. That's the energy picture of gravitational potential energy. And we did the same thing with the spring picture. So if I look at a spring, we could imagine that we have a cart. And this cart is moving here, and what's it going to do? It's going to hit a spring. And what we know here is that as it's coming in, we know that it's going to compress the spring, right? We know it's going to compress the spring. And so if I look at this scenario again, now what I'm going to do here is that I'm going to compress it. So if I look at this guy, it's got to look something like this here now. So now I've compressed the spring. And what does it do? It stops the cart. And so when you're looking at this guy here, then you're seeing that this cart looks like this here. All of the work done to stop the cart gets stored. So if I look at my displacement, you could see that from here to here, I have my D, and I should be more careful here because my D here, I want to make sure I get it in the right direction. It's going to be going in which direction? It's going in that direction. But the force of the spring is in which direction? It's in that direction for the force of the spring. And what we're seeing here is that then the cart does what? It then it re-expands. And as the cart expands, what does it do here? Well, what I'm going to see here is that eventually the cart starts to push this guy all the way back here. And then you're looking at the cart here. But now the cart is going where? It's now going to be going in this direction right here. And as it goes in that direction, we're seeing that now the displacement is going where? It's going from here to there. And the spring force is going what? In the same direction as the displacement. So clearly in this case here, I have work that's negative for the spring. And then in this case, I clearly have work that's positive as I'm going, just like I saw in gravity. And what we said here is that clearly when I look at the network has to be what? It has to be the work due to the compression of the spring plus the work where it expands. And when you look at this, the work to compress it is going to be 1/2 kx squared plus 0. And then the expansion is going to give me 1/2 kx squared minus 0. So you could see that I really have two different things happening. You could see that during the compression, this work is negative. During the expansion, this work is positive, just like we just said right here. But we want the energy picture. And we could see that in the end, this guy is 0, right? This guy is 0. So picture-wise, I want the energy picture. So what do we know about the energy picture? Well, we look at something like this here. And then we need to set up our function here. And as we set up our function, we can see here that I have some, what I called a potential well. This is our energy. So when I look at the work of the spring, we see that it's equal to 1/2 kx squared. That's why we get the symmetric. So now I look at the cart. This is at x equal to 0, where it starts the compression, and then it's going to go to some height here. So if I look at my cart, here's my cart. It's going, and this is where it's just about starting the compression right here. So if I call this A, and I call this B here, you could see here is that now we're talking about the compression of the spring at point A. And so then we know that the cart is doing what? It's moving in this direction, and then it's going to climb up this potential hill until it comes to stop. And then we'll say here, and that this is where it does what? It expands, you get maximum compression here. And then what happens to the cart? Well, it comes back down. So just like this picture up here, right? If we're going up, then that tells us here that this is the direction of gravity while the displacement is this way. Now coming back down here, we see that the displacement has changed direction while the force of gravity is coming down like that. That's the positive work. The same thing happens right here. We know that the displacement is going in this direction, and then coming back down, it goes like this. But then the spring force is going what? It's in the opposite direction here as it's going away. And then here, it's in the same direction right there. So the picture is the same. A conservative force tells us that the energy doesn't get, the work doesn't get lost. It gets transferred into an energy of what? Position. This has to be the work stored in position. And then right here, in this case, you can see here that this is the work stored in position. So you can actually see why the work around a closed path is always zero, because you can see is if I go up and there's no friction, then I'm going to come down at exactly the same speed. That's one of the conditions. That's what it means picture-wise. So now let's go look at condition number 2. So it says this. The work by a conservative force is independent of path and therefore only depends on the endpoint. That's the second condition for a conservative force. And picture-wise, this makes sense, but it's surprising. I think this is super counterintuitive. Okay, so what I want to do here is that I essentially say something like this here. This is what I'm saying. Imagine that I have 2 points, A and B. So I can take path 1 that looks like this. Okay, so this would be path 1. And then I could take a crazy path. Let's take a crazy path that does something like this. And the only thing we see that's in common between path 1 and path 2 is that the work going to A to B, they sure do seem to look different. But if it's a conservative force, what we're saying here is that if I go from A to B, whether it's path 1 or path 2, it doesn't matter. They're exactly the same. So the question is that how do we look at this mathematically? So let's go look at this mathematically. And the way we do this here is that I'm going to assume here a closed system with a ball and gravity. So nothing else can act. So what you're seeing here is that in this scenario here, then I know that the force of gravity should be minus mg in the j direction. So I need a vector this time. Now, what we're going to do here is that we're going to assume two paths. Okay? So we also want to assume two paths a ball can take. So here we go. So the first path, what I'm going to do here is that I'm going to imagine that I have a ball right here. And this ball is going to go to that place right there. So we can see here is that my green ball here looks like this here. So I'm going to take, so this is going to be my path A. This is going to be my path B. And so what you're going to see here is that one of these paths is going to be a direct path. I'm going to call that path 1. Now the other path, I could make it as crazy as I want, but let's try to be nice and clean here. So I'm going to say that this path here goes like this, along that direction. That's going to be path 2. So here we go. Let's set up a coordinate system. Here's my coordinate system. That's my coordinate system. This is y, this is x, this is positive, negative, positive, negative. Okay, now I got my coordinate system. And what do I know? I know that this guy is going to be what? This guy's going to have unit vectors in what? The I direction. And this guy's going to be in the j direction. So I got my unit vectors now. And remember, if I dot opposite, if I dot I dot j, there's no projection, so that's 0. But if I dot I and I or j and j, I'm going to get 1. So here I go. I'm saying that the force of gravity is a conservative force. So if it's a conservative force here, then if I integrate the work from A to B, it should be the same no matter what. Okay, so let's look at this. So the simplest path has to be path 1. So if I look at the work of gravity, I'm going to go from here. So I should label my points here. I did actually, it's A and B. So I'm going to go from A to B. Then I have my force of gravity. Oh, I should be careful here because I should say this is path 1, which I didn't do. And actually, I want to label this a little bit better so it's a little bit clearer. So I'm going to move this just a little bit right here. And then I'm going to call this, I'm going to start off with path 1. So it's just a straight up path. So if it's a straight off path, then this guy tells me the following thing. That it's got to be the integral of the force of gravity, which is going to be minus f of g dy, because we're moving, I should be a little bit more careful. It should be the force of gravity. Sorry about that. It should be this here. So now let's put in our values. Well, this guy should be the force of gravity. And I'm integrating from A to B in the j direction. And if I look at path 1, you could see that it's a vertical displacement. So that means then that this guy is going to be dy in the j direction. Okay, so if I integrate this guy, you could see that the dot products are going to dot each other to 1. So then I'm going to get minus mg. And then I'm going to get the displacement of delta y AB. So far, so good. Now let's go do path 2. So then if I look at this guy, when you look at this guy, note that the path here has multiple locations here. That means it has an X part and it has a Y part. But the force of gravity is still the same, so I still have minus mg in the j direction. But now this has to be dotted into the x part plus the y part. And right away, what you're seeing here is that these two have j dotted with I, and we already know that that's 0. So that x term is 0. And so what I'm really getting here, when I integrate this, I get what? I get minus mg delta YAB. So I get the same result no matter what. And so what this tells us here, even though I have two different paths, I'm seeing here is that the workings between A and B are path independent and only depend on the endpoint. Now I can do the exact same thing with the spring, right? I don't know if you realize, right? Only depend on the endpoints. This is absolutely huge. This is huge. I only have to worry about the endpoints. What do I mean by that? Check it out. So y represents the vertical distance of the ball going up. And you can see, here's my coordinate system right there. Right? So that's what that means. So then check this out. If you don't think this is huge, man, dude, this is like freaking huge. I mean, huge. Let me show you what I mean by that. So this does not depend on the path whatsoever. So let's check this out. As an example, let's do this here. As an example, imagine a frictionless ramp where RJ is sliding down it. Okay. Okay, so here we go. So let's pick 3 different ramps, just to be clear. So here's my first ramp. And then here's a second ramp. And then let's say that this guy goes like this. And then let's check this ramp out like this. So then this ramp goes, right? So if you're looking at all these ramps, what we're going to ask here is the following question. What does the energy look like at the start? So here I go. So I got my slide here. And clearly on the slide, we got RJ sitting right here. And then we want to know when RJ gets all the way down to the bottom, right? His hair is going to be flying this time. We want to know if this point is A and this point is B, in each of these situations here, right? And then let's label this as number 1, number 2, number 3. We want to ask which object, which situation does RJ experience the highest speed at B? Well, here I go. So then what I do here is that I come in and I isolate my system. I'm going to isolate each of these cases. So if I isolate the ramp, RJ, and Earth, then we can see here is that the only force working on RJ is the force of gravity. Remember, it's frictionless, so there's no friction in the problem. So then I come in and I go like, okay, here's my force of gravity. And then I come in and I go like, yep, here's my force of gravity. And I could see that this is the only force acting in the system. So check this out. We don't care, right? We don't care about the path. Because f of g is conservative, then this implies that the work for case number 1 is the same as the work for case number 2 is the work the same case number 3, because it only depends on the endpoints. And therefore, each situation tells me that they have exactly the same kinetic energy. So therefore, they all gain the same speed at the bottom. And you gotta admit, that is crazy. That is really, really crazy. But it's true. That's what it means to be a conservative force.